Hi everyone. When I recorded the lectures for last Friday's class, I didn't hit record until about 5 slides in. So I'm going to re-record those four or five slides and then add them on. I'm going to attach them to the class. So hopefully everything makes sense. In the last several classes, we've been spending quite a bit of time talking about different shapes of molecules, but focusing mostly on molecules that have a single central atom. So that would be looking at a molecule like maybe methane or CO2, and we would talk about the shape of the molecule, we would talk about bond angles and all those sorts of things. What we would like to do is consider more complex molecules that may have several central atoms, and the simplest place for us to start is probably a molecule like ethane, where there's only two central atoms. You might say carbon 1 and carbon 2. And each of the central carbon atoms here we could describe as tetrahedral, bond angles of 109.5. But what we would like to do is talk about the orientation of one CH3 group relative to the other CH3 group. And they are connected by a single bond, and that single bond will have what we call free rotation. So that means that these two methyls can spin around that single bond with very little problem. And at room temperature, think of this as just a molecule that just spins all the time. But let's say that we're able to take that molecule and just stop it from rotating. Let's say we can freeze it and look at just individual possible conformations that you can have. I'm going to introduce this conformation first, and this conformation is what we call the staggered conformation of ethane. So we're going to stop all of our rotation, and when you freeze it like this, if you look at the molecule on the left, we have one hydrogen carbon bond that's pointing straight down, one carbon hydrogen bond on the other carbon pointing straight up, and those can be connected like that. If you were to look at this molecule from the side, like if that's your eye and you're kind of looking at it from that direction, what you would see would be this structure here on the right. We call this structure the ball and stick, hopefully for obvious reasons. The atoms are all balls and the bonds are all sticks. You can draw it instead, if you like, a little more clearly sometimes maybe in this structure, which we just call stick, which probably obvious why we call it stick, right? Balls are gone. Atoms are still there, but we only draw the bonds in, just for clarity. So what we're looking at here is, we're looking at it in that particular direction where you have the front carbon, as I circled there in yellow, and it has one hydrogen that's going up, one hydrogen to the left, and one hydrogen to the right. As well, there's a back carbon, which I'm going to draw like this, which has one hydrogen going to the right. It's got one going to the left, and it's one going straight down. So what we could say is that if you look at any hydrogen on, say, the back carbon, it's sort of halfway in between any two hydrogens, or these two hydrogens that are on the front carbon. So you can see So you can see between these two hydrogens there's a 60-degree angle. Between these two hydrogens there's a 60-degree angle as well. So every hydrogen on one carbon shows up halfway. It's positioned halfway between two hydrogens on the other carbon. So yeah, we give this conformation a name called staggered. We would love to be able to draw a staggered conformation of ethane in 2 dimensions on, for example, a piece of paper with a pen, or in my case, on this iPad screen with an Apple Pencil or a piece of chalk on a chalkboard. Because, while a picture like this might be nice and clear, it'd be very difficult to draw freehand, right? Especially with all the shading and everything. And if I attempted to draw something like that, it would be a hopeless mess that you wouldn't be able to get any information from. So people have devised simpler, cleaner ways of drawing these different conformations. two of which I have drawn here on the right. One's called a Newman projection, and one is called a Sawhorse. And the Sawhorse I don't really want to spend much time on because we don't use that very much in this course, but the Newman projection we'll be using quite a bit. So what we're going to be doing is converting this view that we have on the left to the Newman projection view you see on the right. And what we're going to do is take our front carbon that you see up here, and we're going to draw it on this structure just as this dot. So this dot in the center is a carbon, and it's the front carbon of that conformation you see on the left. That front carbon has hydrogens going left, right, and down. So we would go left, right, and down. And what we do is we draw lines for the bonds, and it starts at the front carbon, right in the very center, and points to those three hydrogens. Now the back carbon, which you can see in the structure here, back here, it's behind the front carbon. We exaggerate its size in the Newman projection, and we draw it as this big circle that you see here on the right. It has three hydrogens coming from it. Don't zoom in, please. It has this one, and this one. So we draw, first of all, the one that goes up, one that goes to the left, and one that goes to the right. So you can tell which hydrogens are on the front carbon because the bond to them extends all the way to the center, dot. And you can tell which hydrogens are on the back because they stop once they hit the back carbon, which is the big ball. So now that we have our Newman projection of ethane, we can start to define relationships between hydrogens on the front and the back carbons. So if you take this carbon that's on the back, HB, there's two others that are on the back as well, the two hydrogens that it's exactly halfway between, which we'll call HF and HF here, those two are separated by 60 degrees. So the bond angle between the back and the front are 60 degrees apart. We say the relationship between those two hydrogens is gauche, and the relationship between these two hydrogens is also gauche. Gauche being the French word for left, although this will have two gauche hydrogens, one left and one right. On the opposite side of that back carbon, there's another front hydrogen down here, which is pointing in the exact opposite direction, right? This is pointing straight down from the central carbon. HB is pointing straight up. And the bond angle between those is 180 degrees. And we would say the relationship between HA and HF that are circled would be anti 180 degrees apart from each other. This is just another view of the staggered conformation in the stick model. So if we wanted to identify the hydrogens that are gauche and anti, the front carbon and the back carbon, we have, let's say, this hydrogen that we have up top. It will have a gauche hydrogen here, a gauche hydrogen here, and an anti-hydrogen here. Okay, we are at the end of the 5 slides that we missed, so we're going to do an awkward transition now into the regular class. I just started the recording. I'm about 10 minutes late on the start of this recording, so I apologize to the people that are going to watch this online. There's going to be a couple of slides that we missed, but maybe I'll add a little bit of something to that after. We're talking about bond rotations. We're talking about ethane, how it can have staggered conformation, where the front carbon and the back carbon are kind of rotated 60 degrees. So in this one, if we were to translate this particular structure that we see on the slide into a Newman projection, what we would do is we would take the front carbon and make a point. The back carbon becomes a big circle over there. The back carbon, if you look at it, has a hydrogen that's pointing straight down. So we would put one straight down. It has one that's coming up off to the right. And we have one that's coming up off to the left. Then the front one has one that's up. one that's down, and one that's down this way. So this would be translating a molecule like ethane, this conformation, into a Newman projection. We're going to be doing a bunch of examples in a little bit, converting a structure into a Newman projection so you see better what that might look like. Okay, so if we do a bond rotation, right, if we take that staggered conformation and we rotate that carbon-carbon bond around just a little bit, you can rotate it to make it look like this, where all of the hydrogens line up, right? So the front hydrogen you see right here exactly lines up with that hydrogen on the back. We call this conformation, this rotational conformation, we call it eclipsed. And the reason is if you look down the carbon-carbon bond, like we said before, all of the back atoms have a front atom that's blocking them. So just like when you see an eclipse of the sun, you know, the moon is in front of the sun, so you can't see the sun. Well, you can see a little bit, but you know, the sun is blocked by the moon in front. Same thing, the back atoms are blocked by the atom that's in the front, and so you can't see them directly. So we call this one eclipsed. This is the second conformation after staggered. The angle between any of the front hydrogens and the back hydrogens is going to be 0. Right? They're going to be exactly overlapping with each other. So to convert this to a Newman projection, it's going to look something like this. And, you know, ideally, those hydrogens would be exactly overlapping with each other, but that makes it super messy looking. So what we usually do is just offset the back one just by like a few degrees, just so we can tell that they're sort of exactly in front of one another. Okay, so these are all eclipsed. So what you can do with ethane is you can spin those carbons around and around and around. And as you spin it, you're moving from a staggered conformation to an eclipsed conformation to a staggered conformation to an eclipsed as you sort of rotate it through 100 or 360 degrees. So they start, they stop, they start, they stop as they go. So imagine this first structure right here, one on the top left. It's just ethane, but I've colored 2 of the hydrogens yellow. In that conformation, we would say the angle between those 2 hydrogens is 0 degrees. They're exactly eclipsed, they're exactly overlapping. And then as you rotate it around, when you get to 60 degrees, you get this conformation down below. Again, for reference, just look at the yellow ones. They're just same as the other hydrogens, I just colored them so you'd identify them easy. And then if you rotate another 60 degrees, you come to this one. Another 60 degrees, you come to this one. And you keep sort of rotating alternately back and forth between staggered and eclipsed conformations. What we know is that there's an energy change, there's an energy difference in the molecule when you rotate it around and go between these high points and low points. It turns out that the most stable conformation is one where the hydrogens are perfectly staggered. So all of the 3 staggered conformations that you see drawn out on the bottom, those are the most stable conformations. And ideally, if the molecule had no energy, wasn't able to spin, had nothing causing it to rotate, it would prefer to be settled into one of those lower energy conformations. But it does have energy, it's colliding in solution, there's heat, there's all kinds of things going on, it's very active, it's colliding with other things, those things are spinning like crazy. And what you see is you can also go through these higher energy conformations, even though maybe they're not preferred, they're possible, and they're about 12 kilojoules per mole higher in energy. Now here's a good question. Does that number mean anything to you at all? 12 kilojoules. Is that a lot or a little? Any guess? I heard a guess of a little. Well, to put this into context, how strong is a carbon-carbon bond? There's one you probably don't know. It's like 350 to 400 kilojoules. So imagine you have a molecule with a CC bond and you want to like pull it apart and break that carbon bond. You would need about 350 to 400 kilojoules to do that for 1 mole. Here, we're just trying to spin it. We only need 12. That's not very much at all. So at room temperature, there's all kinds of energy in there. These are all bumping around. They're rotating. They're vibrating. We know they're vibrating from the IR chapter. All these things are going on in solution. So 12 kilojoules is not much of a barrier. This is happening very, very quickly. Very, very commonly, these things are just spinning around all the time. But we do know the staggered conformations are more stable than the eclipsed conformations. Okay, why is this the case? Well, there is various types of strain that can exist in a molecule. We're going to discuss 3 of these. And one of these is called torsional strain. And this is the strain that we give to describe what happens in a molecule like ethane. When this molecule is in an eclipsed conformation, like the one that we're drawing here, what we can say is that the electrons that are in this single bond and this single bond are as close to each other as you can get them. Those electron pairs in those bonds repel each other. If you rotate it away from the eclipsed into this staggered conformation that you see over here, the electrons in those bonds are a little further apart. So the, I guess, repulsion that you see between these ones, we call torsional strain. There's torsional strain in both of these, but there's less torsional strain in the staggered. So the staggered is the preferred conformation, because that reduces the torsional strain. Great. By the way, if I write things out like this in all caps, it's not because my cap key got stuck. It's important. Let's go bigger. Okay. Here's a molecule of butane. Butane has 4 carbons, and I've numbered them here, 1, 2, 3, 4. We're going to look down the 2-3 bond, carbon 2 and carbon 3. You see carbon 2 here and carbon 3. And so what I'm going to do is rotate it around so it looks like this structure you see on the right. And what I'm going to do right now is I'm going to switch over to the drawing app. And what I'm going to do is convert that into a Newman structure, a Newman projection. So we had carbon, 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 hydrogen, hydrogen. That's a CH3, CH3, hydrogen, hydrogen. That's carbons 1, 2, 3, 4. So we're going to like put our eye over here, right? And we're going to be looking kind of down the 2-3 bond. And if you do that, what happens is carbon 3, remember, is the back one. Carbon 3 is the big one. So we're going to draw a big one for carbon 3. Carbon 2 is just a little point in front that looks like that. So if you're standing here like this, right, and you're looking in at carbon 2, which direction would it look like the methyl is pointing? Up, down, left, right? Down. Yeah, imagine that you're here, you know, your nose is here, your nose is down, so is that methyl, relative to carbon 2. So on carbon 2 here, we would draw a CH3 that's down. And the other 2 positions are going to be hydrogens that one's up to the left, which is this one. One's up to the right, which is this one. Now on the back carbon, which is carbon 3, which we draw as a big thing, the methyl is pointing which way? Up, yeah. So if you're looking at it from that vantage, from side on, that methyl will be up. And what about the other 2 hydrogens? One will be down here, and one will be down here. Okay. Is this a staggered or an eclipsed conformation? Staggered, good. This one's staggered. What would we say the relationship is between the two methyls? Anti, good. Come back. Anti. What's the relationship, say, between these two? Gauche. Okay, perfect. So that's this conformation of butane. This is the Newman projection that we just produced. We can rotate that around, right? We can rotate it as well. We can rotate the carbon-2, carbon-3 bond, and we can make this conformation as well. Is that a staggered or an eclipsed? This one is staggered as well. And now the two methyls are gauche to each other. They're not anti like they were in the previous one. So this is just another possible conformation of butane. And of course, there's a bunch of eclipsed ones as well. Is that the same slide? Yeah. So here's an energy diagram that shows the rotations of the C2 bond, all the different conformations that you can get, and the energies of each of these conformations. The lowest energy one, which is right here, right in the middle, that lowest energy conformation is the one that we drew first. That's the one where it's staggered, first of all. Remember, we like staggered because staggered minimizes torsional strain. Also, the two methyls that are on carbons 2 and 3 are anti to each other, right? So these two are anti, we would say. We have two other staggered conformations where the two methyls are gauche. They're not quite as stable though. They're a little bit higher in energy, 3 kilojoules per mole, which is peanuts. You know, that's nothing, 3 kilojoules, but it's something. We can measure it, and so it's just a little bit higher in energy. Now if you look at the high energy, the maxima here, the high energy conformations, they're all, first of all, eclipsed. So we know they're all bad because they maximize the torsional strain. But not only that, you know, there's these two, which aren't so bad, but then you have these conformations that are a lot higher in energy. These are the ones where the two methyl groups line up with each other. And you can see kind of in this picture right here, do I have it drawn here? No. So I'm going to draw what that looks like as, so that would look like this conformation where you have hydrogens. The Newman projection of that really bad high energy one would look like this. Okay. So this one we would say is eclipsed. This maximizes the torsional strain because all the bonds are lined up, but also it puts the two biggest groups close to each other in space. So imagine these molecules, you know, these CH3s, these have electron clouds around them. They have orbitals with electron density in there. Kind of think of them as like, I don't know, like big Nerf balls, right? Imagine like the atom is like a Nerf ball and it's squishy. You can push it around. We know you can kind of shift the electron cloud a little bit. Back when we talked about dispersion forces, you can kind of manipulate that electron. It's not a hard ball. It's kind of a squishy ball. Well, when you put those two methyls close to each other, imagine you're taking two balls and you're kind of squeezing them together. You can force them together, you know, but they're going to repel. If you let go, they're going to push away from each other. That's what happens with these methyls. It can get into a conformation where they're close to each other, and then the balls start to kind of overlap and squish each other a little bit. But if you let it go, it kind of wants to spring away into a lower energy conformation. It wants to rotate away to get those methyls far apart from each other. So we have a name for this. It's called van der Waals strain. So van der Waals strain is the second kind of strain we're going to be looking at. Van der Waals strain is a strain you find in a molecule where you take two groups and you kind of force them to be in the same region of space. You don't let them spread out and take up their own space. It's like taking those Nerf balls and squeezing them into the same volume. They don't want to be there. They want to spread out.
So van der Waals strain gets higher or more severe the bigger those groups are, and the closer you try to squeeze them together. Right? Consider those Nerf balls again. If you have two little kind of hard balls and you kind of push them a little bit, but if you have great big ones and you really try to squeeze them in the same volume, then it becomes very problematic. So for that reason, anti is the best structure you can get, because it takes those two bigger groups that are on the central atoms and it positions them as far apart from each other as is possible. They're completely pointing in exact opposite directions, so this minimizes van der Waals strain by putting those methyls as far apart as possible. Gauche is a little bit worse, right? The methyls are kind of getting a little bit close to each other here. They don't want that. And so for that reason, gauche is not going to be as stable as anti. But the absolute worst is eclipsed, where you put the two methyls right on top of each other. There, this one's the worst one. This is the highest energy conformation, least stable. Does not like to be in this conformation, because these two methyls, you know, they're drawn here as sticks, but in reality, they're kind of like big clouds. Or here, they're kind of getting in each other's way. They're squishing together like Nerf balls. And so it wants to twist this bond. It wants to rotate around to get them away from each other and minimize van der Waals strain. So when we draw alkanes, alkyl chains, you see me drawing them like this all the time, right? Zigzags. Why do we use zigzags? It's because when you draw them with zigzags, every carbon-carbon bond has the big things on the other side anti to each other. This kind of a structure for a chain minimizes van der Waals strain, minimizes torsional strain. All of the carbons are staggered. All of the carbons have the biggest groups positioned opposite the other big groups. Okay, so this is why we like to draw them with zigzags. That's the best conformation for an alkane chain. It doesn't mean it's the only conformation. As I said, if you have a container and you're full of, say, decane, where it's all 10 carbon chains, every one of these bonds can rotate, right? They're all rotatable. We have lots of energy in there at room temperature. They're all bumping around, they're rotating, they're spinning and vibrating. So it's not like every single molecule is going to be in this straight as an arrow conformation. It's going to be a bunch that are curved or balled up or whatever. But what happens is you start lowering the temperature and you take some of that energy out, more and more of them are going to adopt that most stable conformation. Okay, so we like to draw them as zigzags. We like to maximize the anti-relationships between larger groups, and we like to go with staggered conformations. Perfect. So now we know two kinds of strain. We know van der Waals strain and we know torsional strain and the difference between them. We're going to introduce a third one, and what we're going to do is move into cycloalkanes. And it's important that you guys have in your minds the ideal bond angles for sp, sp2, sp3 carbons that we tested this week. And I think we went through that in quite a bit of detail. These are a bunch of cycloalkanes that exist. You can go buy bottles of these things from chemical supply companies. I have several of these in my lab. All of the carbons in all of these cycloalkanes have what hybridization? Every single one of these. All of them are sp3. All of them have 4 bonds. What's the ideal bond angle for sp3? 109.5. There we go, 109.5. I asked this question many times yesterday. 109.5. Now, look at all these shapes. How are you going to make, for cyclobutane, 109.5? That's a square. What are the bond angles in a square? They're 90, right? What about this? A triangle, an equilateral triangle. 60. 60 is not 109.5. So what's this mean? Well, when we say 109.5, what we say is ideal bond angle, right? Methane has ideal bond angles because it has a carbon, it has small little bitty atoms, it has hydrogens. They can all spread out. They're all the same thing. they can all spread apart equally, and you can have 109.5. If you could take a molecule of methane and blow it up to something you could hold in your hands, let's say it's 2 feet wide, you could take two bonds, carbon-hydrogen bonds, and you could pry them close to each other. You can bend these bonds, you can change those angles, but that's going to increase the strain. And if you let go, they'd snap back to 109.5. So what we know is that you can create strain in a molecule by forcing the bond angles to be something other than the ideal bond angle. So something like cyclobutane, we can kind of take these atoms and we can kind of, take those bonds and stretch them. I mean, obviously we can't grab them with our hands and stretch them, but we can make these molecules in other ways. You can have sp3 carbons with bond angles of 90 degrees. And when you do that, you're introducing strain. We call it angle strain because the angles aren't right. Sometimes we also call it ring strain. Ring strain and angle strain are the same thing. I think angle strain is a better word because you can have angle strain in compounds that don't necessarily have rings. But if you make these ring structures, especially that cyclopropane, especially 60 degrees, there's a tremendous amount of ring strain in there. So think about all those carbons. They're all sp3. They all want to have bond angles of 109.5, but because of the shape of the molecule, they're strained in. It's like a loaded spring. And imagine you have a big cyclopropane, and you took a pair of scissors and snipped one of the carbon-carbon bonds. It would flip open and release all that energy as heat. Okay, it would cause other vibrations and so on, and it would cause kinetic energy in the solution. So yeah, that doesn't like to be constrained like that, but because the barrier, the activation barrier is high for it breaking, carbon-carbon bonds are strong, it stays as a nice stable molecule. But if you give it a chance, if you do something, if you burn this, you're going to get a crap ton of energy out of cyclopropane. Now, back in the 19th century, over 100 years ago, 120 years ago, people didn't have the same understanding that we have today about the structure of all these molecules. They didn't know the ideal bond angles. They didn't know orbitals and all this kind of stuff that we know today. It's all a new invention. It's all about 100 years old. Like Lewis structures were born in 1918, right? So that's 102 years ago, which is like on the scale of human knowledge, a drop in the bucket. Like there's people alive today who were alive when Lewis structures didn't exist, if that makes you feel like you're young. Maybe to you guys 1902 sounds like a crazy amount of time ago, but yeah. At that time, they thought all these cycloalkanes were just flat shapes in 2 dimensions. So if you assume they're all flat, these are the bond angles that you get. And so if you look at which of these should have high ring strain and low ring strain, cyclopropane should be really bad. 60 degrees is very far away from 109.5. Cyclobutane is better. 90 is closer, but still kind of far away. Cyclopentane, actually, look at that one. 110. So if you just have a perfect, what's that called, pentagon? Perfect pentagon, all the angles are 110 degrees. That's pretty damn close to 109.5. So this should have very low ring strain. Then we have 120, which is getting off. That's more sp2 territory, but we're not, we're sp3. Cycloheptane and so on, and you can see the angles get larger from there. So if you just looked at those bond angles, we would expect cyclopentane to have the lowest ring strain, and therefore we might guess that cyclopentane would be the most stable way of making a ring of carbons. That 5 might be best because it has angles that are closest to what it wants to have anyway. So what we're going to do is burn these guys. We're going to burn them and use heats of combustion. We can experimentally measure stabilities, remember, using heats of combustion. We did this before for branched versus not branched alkanes. Well, if you burn all of these, this is the energy you get out of them. Not surprisingly, as you add carbons in, the heat of combustion goes up. So you can't just look at the numbers as they are, because this isn't telling you anything about stability. It's telling you how many carbons there are in the ring. more carbons, you get more energy out when you burn them. But what we can do is, because each of these compounds is just CH2N, right? For this one, N equals 3, N equals 4, and so on. What we can do is just divide each one of those by the number of carbons in the chain, and we're going to come up with combustion per CH2 in the molecule. So we're just going to take these numbers, which came out of a bomb calorimeter. We're going to divide each of those by the number of carbons in the ring. And when we do that, we get something like this. Least stable cyclopropane. Surprise, surprise. We know cyclopropane has the highest ring strain because it has really bad bond angles of 60 degrees as opposed to the ideal of 109.5. Cyclobutane is quite a bit better than cyclopropane, but still second worst. Cyclopentane, remember, this was our golden child. This was the one that we thought was going to be the most stable because it had 110, and we want 109.5. It was pretty close already, but it's not the best. It's not the most stable. Best is actually cyclohexane, which you may have seen a lot of compounds that I'm showing in class and on the test yesterday that has 6-membered rings, 6 carbon rings in them. Very, very common in biology. Biology has caught on that cyclohexanes are stable, and there's tons and tons and tons of molecules with 6 carbon chains in biology. Sugars are actually all 6 atom chains, with one of them being oxygen. Actually, there's some pentoses as well, so there's 5 and 6. But cyclohexane is the most stable of all the cycloalkanes on a per CH2 unit. So it's minimizing the strain somehow. Then it goes back up when you go to heptane, octane, nonane, decane. You know, these are both the same. Cyclohexane is the best. And this may not make sense right away if we consider all of these as just flat 2-dimensional molecules, just flat shapes. Well, can you guess where I'm going to go? These are generally not flat shapes. They have a 3rd dimension they can bend into, right? Imagine you're trying to make something flat, it can flip up, right? It can occupy that 3rd dimension as well, and it will find the conformation naturally that's lowest in energy. So cyclopropane looks like this. Cyclopropane doesn't have a lot of choice, right? It's got 60 degrees, really bad angle strain. Also, if you look down, any 2 carbons, like if we call this carbon 1, 2, 3, rotate it just a little bit, 1, 2, 3, so that you're looking, you know, carbon the back one, carbon 3 is the front one. Is that eclipsed or staggered? That's eclipsed, right? Because these hydrogens on the front and back perfectly line up. In fact, every hydrogen on this molecule is eclipsed with ones on the right side and ones on the left side. These CH2s are eclipsed all the way around the ring. So not only does this maximize your angle strain, it also maximizes torsional strain. It's got 2 strikes against it. It's got 2 types of strain. Van der Waals strain we don't have to worry about here. There's no big groups attached, just little hydrogens. We don't worry about van der Waals for small things like hydrogens. But this has 2 strikes against it, this structure, cyclopropane. So this causes it to be unstable, which is why it was the highest in energy out of all the cycloalkanes we looked at. Cyclobutane has the same problems. It still has all the CH2s eclipsed, but the bond angles are a little bit more forgiving here. And so the angle strain is down from cyclopropane, which makes this more stable. What can happen too is this ring can pucker. So imagine taking this sort of square, and I don't know if you can see with my hands here while I'm holding that for sure. That's not even close to a square. But imagine it kind of goes, if it's flat, it kind of goes like that. It puckers up. It puckers into the 2nd dimension. Maybe it looks something like this, you know, where, you know, this carbon has puckered up and this one's up and these 2 are kind of down. If it puckers, what happens is your bond angles get a little bit worse. You get angle strain that increases a little bit because 90 is sort of the best you can do here. But on the other hand, what you're doing is you're making the adjacent hydrogens not eclipsed anymore. They're not perfectly staggered, but they're a little bit better. So this conformation is, slightly better, but the difference is very small between a perfectly flat and the puckered. Puckered is worse for angle strain, but better for torsional strain. It was a bit of a toss-up which two of those is best. So what we're going to do, by the way, this is if you happen to have those 3D goggles. These are the red-blue ones that used to ship with comic books. I used to have a class set, and so we would look at a lot of these compounds in 3D as well, and you can actually see the three-dimensional structure. It's unadvisable to distribute those during COVID, so apologies, but if you have one, for whatever reason. Cyclobutanes, they're very, they have high strain. They're hard to make. They're actually really hard to make in the lab. They're one of the hardest types of rings to make, but we have ways of making them. Biology knows how to make them. This is a fatty acid that's found in a certain type of bacteria, and they have a special structure. They have a organelle, I guess you'd call it, called an anamoxisome. And the anamoxisome has hydrazine in it, and hydrazine is a super toxic chemical. It's like NH2 single bonded to NH2. Very, very toxic for living things and cells, but it needs it. And so what it does is it creates a membrane around it that's super difficult for the hydrazine to escape out into the cell. And it uses this really weird fatty acid that has this, series of cyclobutanes that are attached to each other. These are called lateranes because if you look at it from the side, it looks a bit like a ladder. And those are extremely dense. These don't rotate. They're not floppy or flexible at all. They pack together super tight, and they make a really impervious membrane around that organelle and prevents the hydrazine from leaking out. So some very fascinating compounds that you can find biological systems produce. Cyclopentane, next one up. We're going 5. There's the flat version. We call it planar. Planar just means all the carbons are in one plane. Planar's good from an angle strain perspective because all the angles are 110, very close to 109.5. Problem with planar, though, is when you line all the carbons around like that, if you look at any two, the hydrogens are all eclipsed. So planar is really bad from a torsional strain perspective because it eclipses all of the hydrogens around the ring, but it's great from an angle strain perspective. You can have envelope, where you kind of take one corner and pull it up a little bit, and that maybe adds a tiny bit to the angle strain, but it causes the hydrogens on these 3 carbons to now be staggered, which is great. So the envelope is a little bit better. There's also this other kind of weird one called a half chair. There's a bunch of sort of different conformations here. They're all it's a toss-up again, similar in energy. They're all kind of rapidly interconverting. There's not a clear winner out of any of these 3 conformations. Now, we first guessed that this might be the most stable cycloalkane, but it turned out cyclohexane was the best. So we're going to look at cyclohexane, which is the lowest one,